Today we're going to look at some nice objects related to the Riemann zeta function. And so this is like one of the most famous functions in mathematics going around right now. And it has like applications in analytic number theory, or I should say that it arises out of the study of that subject. So let's recall what this function is. So zeta of s is equal to the sum as m goes from 1 to infinity of 1 over m to the s. That expands out to 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s, and so on and so forth. And so using methods from Calculus 2, you can determine where this converges. So it'll converge for values of s where the real part is bigger than 1. Also, this thing famously has a so-called analytic continuation, which we won't talk about here. And so here's a really important fact about the Riemann zeta function at even natural numbers. And that is, for all natural numbers n, zeta evaluated at 2 times n is equal to a rational number times pi to the 2n. So this is a really nice result. And so here are a couple of examples of that. Zeta of 2 is pi squared over 6. That's in fact the famous Basel problem. We've made a couple of videos of different solutions to that problem on the channel before. Zeta of 4 is pi to the 4th over 90. I think we've got a video about that. Zeta of 6 is pi to the 6 over 945. I don't remember, but maybe we have one of those as well. Zeta of 8 is pi to the 8 over 9,450. You might think that a pattern is going here. Maybe it's always pi to the 2n over something, but that'll break down with zeta of 10. Go ahead and look that up if you'd like to. And so, given this fact, I think the following sums are interesting. And these sums are built from taking just these rational numbers. And so maybe get rid or divide out those powers of pi. So maybe just the straight up sum of those rational numbers. So 1 over 6 plus 1 over 90 plus 1 over 945 and so on and so forth. I think that's an interesting object. And then the alternating sum is also an interesting object. And we're actually going to determine the value of this alternating sum, and we get a really nice result. You get an also kind of nice result for this regular sum, but you can attack the regular sum very, very similarly to this alternating sum. Okay, so how could we maybe write this down a little bit more carefully? Well, perhaps we would write it like this. So this 1 over 6 could be rewritten as zeta of 2 over pi squared. Because that's exactly what we're doing. We're dividing out the pi squared. And then this 1 over 90 would be zeta of 4 over pi to the 4. And then this next term will be zeta of 6 over pi to the 6. And then you can probably see the shape that's happening here. And so now we can maybe formalize our goal a little bit more easily. And so our goal will be to find the sum as n goes from 1 to infinity of minus 1 to the n plus 1 times zeta of 2n over pi to the 2n. So that encodes this alternating sum down here. Okay, well, kind of fortunately but unfortunately, we need a pretty powerful lemma in order to find the value of the sum, but we will derive it. Okay, so let's get to that. Okay, so that special lemma we need, it goes like this. This could actually be a video all on its own, but we'll prove it as a lemma for this video. So the sum over all integers of 1 over m squared plus a squared, where a is non-zero, is equal to pi over a times the hyperbolic cotangent of pi times a. So I think that's a pretty nice result. Okay, so how can we do that? Well, we're going to do it by considering the following function, and that'll be the hyperbolic sine of z over z. And we're going to look at the zeros of this function. So what are the zeros of this function? Well, we're going to use the fact that this has the zeros of sign almost. It has the zeros of sign multiplied by I. But of course, we just like factored out the 0 at z equals 0. So it has all of them except for those. So in other words, the zeros are z equals, let's see, k times pi I, where k runs through all integers. And now we're going to essentially factor this, thinking of it like a polynomial, but we're just going to factor all the zeros out. And this may seem kind of sketchy, and we're not going to make it careful in this video, but you can make this process be defined a little bit more carefully, and you get something called the Weierstrass product. Okay, so again, that's going to give you something nice like this. So we've got 1 minus z over pi times I. So that's like for the 0 at z equals pi I. In other words, k equals 1 right here. And then next we would have 1 plus z over pi I. And so that would be for the 0 at negative pi I. So in other words, k equals negative 1. And then we'll extend this, or we'll keep factoring this in these pairs. So 1 minus z over 2 pi I, and then 1 plus z over 2 pi I, and then so on and so forth. But now the idea is to smush all of these pairs together, because essentially we've got something that looks like, well, it's actually a sum of squares factorization using complex numbers. So these first two will multiply together to give us 1 plus z squared over pi squared. The next two, 1 plus z squared over 4 pi squared. I bet you can guess what the next one is. It's 1 plus z squared over 9 pi squared, and then so on and so forth. So if we could put this together into product notation, this will be the product as k goes from 1 to infinity of 1 plus z squared over k squared times pi squared. Okay, so that's looking pretty good, but infinite products are kind of difficult to work with, so maybe we'd like to work with infinite sums instead. And we can turn a product into a sum by taking the natural log. So taking the natural log of the left-hand side will give us the natural log of the hyperbolic sign minus the natural log of z. Using that difference rule for quotients, will give us the sum now as k goes from 1 to infinity of the natural log, well, of this stuff. So 1 plus z squared over k squared times pi squared. Okay, now let's bring that formula up and then we'll move on. So this is where we left off. I moved that natural log of z to the other side of the equation, but that's all. And so let's recall our goal over here is to get to the hyperbolic cotangent. And we can get that by taking the derivative. Well, that's in fact why we looked at this function in the first place and why we took the natural log. Because the derivative of this will in fact be that hyperbolic cotangent. But I think we need to get there. So let's say this arrow is taking the derivative. So by the chain rule, we'll have the hyperbolic sign in the denominator, and then we'll have the derivative of that, which is the hyperbolic cosine in the numerator. Then taking the derivative over here, we'll have 1 over z, and then here we'll have the sum as k goes from 1 to infinity. So let's see, that stuff is going to go into the denominator, and then we'll have something in the numerator which is its derivative. So in fact, we'll have 1 plus z squared over k squared pi squared. Then in the numerator, we have the derivative of that. So that'll be 2z over k squared pi squared. But that's a little bit gnarly to look at because it has like all of those fractions in there. So let's multiply the numerator as well as the denominator by k squared pi squared. And that'll leave us with 2 times z over, let's see, we'll have z squared plus k pi, the whole thing squared. Okay, so now let's rewrite that. I'll bring this 1 over z down, and then I'm actually going to split this into 2 sums, but those sums are going to be the same. So we're going to have the sum as k goes from 1 up to infinity, and now we'll just have z over z squared plus k times pi squared, and then we'll have another sum. Again, it'll go from k equals 1 to infinity of the same thing, z over z squared plus k times pi squared. So nothing fancy happened there. But now let's notice that every appearance of k, which is the index of summation inside of that sum, is in fact squared. So I can actually re-index this by exchanging k with negative k, and nothing changes except now my sum goes from minus infinity up to minus 1. Okay. Oh, but now let's take this 1 over z and rewrite it a little bit. And we're going to rewrite it as z over z squared plus 0 times pi squared. But now look at what we have. We have the same object in 3 different places. This is the 0th term. These are the terms k equals 1 to infinity, and those are the terms k equals minus 1 to infinity, or minus infinity to minus 1. So now we can push those all together, and we'll have, in fact, the sum over all integers of, well, it's going to be z over z squared plus k times pi squared. So something like that. But now let's maybe extend this off the other side as well and go ahead and write that as the hyperbolic cotangent. So we've got cot h of z. And now where would we go from here? Well, at this stage, I'm just going to set z equal to pi times a and then multiply by pi over a, and then we'll have it. Let's see. We'll have pi over a times this hyperbolic cotangent evaluated at pi times a is equal to, well, let's maybe write it out. So we'll have pi over a times, now it'll be the sum as k goes over all integers of, well, we've got this pi over a in the numerator, and then in the denominator, we'll have pi over a squared plus k times pi squared. But now from here over to here is simply a matter of replacing the k index with an m index and then canceling some things out. I'll leave that for you. Okay, so now that we've got this very powerful tool built, we can jump into our main. Okay, so we finished our limit, now we're ready for our main goal. And I'm going to rewrite this a little bit. So I've got my sum as n goes from 1 to infinity. I have, well, maybe let's bring this minus sign out front, and then I'll have minus 1 over pi squared raised to the n power. So that takes care of the minus 1 to the n plus 1 and the pi to the 2n. Now I just need to take care of the zeta function evaluated at 2n. But I'm going to do that by using the definition of the zeta function. So now I have the sum as m goes from 1 to infinity of 1 over m to the power 2n. And now we're going to do our favorite trick of exchanging the order of summation. So I'll keep this minus sign out. Front, and then I'll have the sum as m goes from 1 to infinity of the sum as n goes from 1 to infinity of, well, actually now I can put a bunch of stuff together. Minus 1 over, let's see, we've got m squared pi squared, so I'm going to write that maybe as m pi all squared and then raised to the n power. But the great thing here is now we can view all of this as a geometric series. Because if we kind of forget that we have this outside sum with respect to m, well, that's exactly what we have on the inside there. And it's in fact a geometric series where the starting term and the common ratio are both negative 1 over m times pi squared. So we can apply the standard summation rule for a geometric series. That's going to give us, well, we've got this minus sign out front, and then we have the sum as m goes from 1 to infinity of, well, we've got the starting term, minus 1 over m times pi squared over 1 minus the common ratio, but that's going to be 1 plus 1 over m times pi squared. Okay, nice. But check it out, this minus sign right here can cancel this minus sign right here, and then we can bring that m times pi squared to the denominator, and that'll leave us something like this. So we'll have the sum as m goes from 1 up to infinity of 1 over, let's see, m times pi all squared plus 1. But notice that's not exactly the format we need over here. We need this to be m squared plus something. But that's not what we have. But we can get there by dividing a pi squared out of the denominator. So let's do that. So that'll leave us with a 1 over pi squared out in front of everything. And then we'll have the sum as m goes from 1 to infinity of 1 over m squared plus 1 over pi squared. And now it's starting to look like this over here. The one thing that we need to do is build this up from a sum m going from 1 to infinity to a sum over all integers. So we can do that by noticing that m here is squared, so I can actually split this into two sums. I'll do that by putting a 2 down here, and then I'll add on the same sum here, but now that sum will go from m equals minus infinity up to minus 1. And then, like I said, it's the same thing. M squared plus 1 over pi squared. Great. But now we've got almost all of the sum over here. All that we're lacking is the 0th term. Let's notice if we plug in m equals 0, we get pi squared. That 1 over pi squared in the denominator flips up to the numerator. Okay, but you know, that attached to this 1 over 2 times pi squared will end up being a half. So that means we're going to add a 1/2 in, and that means we also have to subtract a 1/2. And then let's note that these are both the m equals 0 term. Okay, so now let's package this all together. So we have 1 over 2 times pi squared, and now it'll be the sum over all integers m of 1 over m squared plus 1 by pi squared, and then we have to subtract that half off. But now we can use our formula over here, this thing right here, where a is 1 over pi. So let's see, we still have this 1 over 2 pi squared out front, and then we'll have pi over 1 over pi, so that ends up being pi squared. Well, that's actually kind of nice. And then we'll have the hyperbolic cotangent of pi times 1 over pi. Well, that's just the hyperbolic cotangent of the number 1, and then we have to subtract off our half. Okay, good. Well, now clearly this pi and this 1 over pi squared cancel. We can take the half out front, and we'll be left with this hyperbolic cotangent of 1 minus 1. But that could be our final answer, but there's actually a nicer form. So let's maybe finish it off on the next board. So this is where we are so far, but I'd like to simplify it even more. And in order to do that, let's recall the definition, or at least one of the definitions of these hyperbolic trigonometric functions. So hyperbolic sine of z is half times e to the z minus e to the minus z, then hyperbolic cosine is essentially the same, except that minus sign is replaced with a plus sign. Then the hyperbolic cotangent, which will be the hyperbolic cosine over the hyperbolic sine, well, it simplifies down to this right here after the halves cancel. So that means we can apply this rule. So this will be a half, which, you know, we got from that. And then we'll have e plus e to the minus 1 over e minus e to the minus 1, and it'll be minus 1. But let's maybe put this minus 1 with the same denominator. So e minus e to the minus 1 over e minus e to the minus 1. So there's our number 1. And now let's see what stuff cancels and see what stuff stays. So notice this e minus e will cancel, and we'll be left with e to the minus 1 minus e to the minus 1. Those will double up. Oh, but they'll double up and cancel this half, leaving us with e to the minus 1 over e minus e to the minus 1. But I think it's pretty alluring to take this and multiply the numerator and the denominator by e, leaving us with 1 over e squared minus. So this nice sum involving pi and the Riemann zeta function also gives us Euler's constant. There's a lot of cool stuff happening in this sum. Now, if you've stayed this long and you haven't subscribed yet, maybe consider subscribing. It helps the channel out a lot, and that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.